So today we're going to be talking about vectors, and what vectors are basically just mathematical structures that are used to measure both magnitude and direction. And you may have run across vectors if you've taken any physics classes, because they're fairly important there. And vectors are important because they, again, factor in these two different components, and that's in contrast to scalars, which is another mathematical structure, except they don't factor in direction, they only factor in magnitude. So we have vectors, and we have scalars. And the difference, again, is that scalars only factor in magnitude and vectors factor in both direction and magnitude. And for those of you who don't know, magnitude is just how big something is, or how long or how great something is. So you can kind of think of magnitude by remembering earthquakes, because earthquakes are measured by their magnitude. So a magnitude of an earthquake just measures how big the earthquake was, just like how magnitude in mathematics just measures how big or how long something is. So examples of vectors include measures like velocity and force, while scalars include measures like speed and distance. And I think the clearest difference between vectors and scalars can be seen between if you compare velocity and speed, because they both measure how fast something is going, except the difference is that velocity factors in the direction while speed does not. The same thing kind of applies to force, where you're not just measuring how much force is being applied, but also what direction that force is being applied, while with distance, you're just focusing on how big the gap is between A and B, and not necessarily what direction that gap is facing. So let me get a different color, and let's move on to this this representation here. And when we look at vectors in two dimensions, which is what we're going to do today, is we look at them on a coordinate plane, just like we'd see any line, except we use different notation and we represent them using arrows. So in this case, we could figure out the magnitude of this vector being represented on the coordinate plane by looking at how long the vector is, so how big the vector is. And so that's our magnitude, so I'll just write mag. And then we can figure out the direction of the vector by looking at the angle at which it is facing. So the angle is always measured relative to the x-axis, and it's always going to be the smallest angle measure between the x-axis and wherever the vector is facing. So we both have magnitude and direction, and then we have a vector. As you may see here, we have this kind of funky notation here to represent this vector. The vector. And so when we talk about a vector, we usually represent them by a letter, and then we further represent them through this notation, which is called component notation. So A, comma, B. So we have vector V being represented through the components A and B. And the components are just these two numbers here, A and B. So we figure out what the components are on a graph by looking at what the terminal and initial points of the vector are, or the arrow are. In this case, the terminal point is A and B, so that's where the vector ends, which is right here. And we can look at the initial point, which is the origin, which is here, and that's where the vector begins. That's where the tail is. So we can figure out the components A and B by subtracting the value of the initial point from the terminal point. So it would be the x value of the terminal point minus the x value of the initial point, and the same thing for the y values. So we get A and B here by doing A minus 0, because it's the origin is 0, 0, comma, B minus 0. And so if we were to use initial point that wasn't the origin, we'd have, like, for example, 1, 1. We'd have A minus 1, because that's the value of the x, that's the x coordinate, and then B minus 1, because that's the value of the y coordinate for the initial point. And so that's basically how component notation works. So if we were actually going to try to measure this thing, we're going to measure how long this magnitude is, we'd actually be utilizing the absolute value of the vector. So let me do a different color. So we'd have the absolute value of vector V. And for those of you who are familiar with physics or have taken this class, wink wink, we'd know that we can figure out the speed of an object by figuring out the absolute value of the velocity of that object. So the same thing applies with here, because again, speed is just the magnitude of a velocity. The same thing applies here, except we use this equation where we have the magnitude is equivalent to a squared plus b squared. So we take the squares of each of these components and then add them together, and then take the square root of that to figure out the overall magnitude or the overall length of this vector here. So now that we have just kind of vector notation down, now we can figure out what the magnitude of a vector is. We can now start doing operations with vectors. And so say we wanted to add a vector, so let's say we had a vector A, and we wanted to add it to another vector, vector B. The way we do that is, well, first of all, we'd get the notation, or the component notation of A and the component notation of B, and say, let's just put it hypothetically as, so A, or let me do that differently. So A is equivalent to component notation x1, comma y1, and then B is, let me do magenta. Okay, let's do B is equivalent to notation x2, comma y2. And if we're just going to add these together, it's actually fairly straightforward. All we need to do is just add the corresponding components together. So we have, so we'd add x1 and x2 together, and then y1 and y2 together to get what the new vector is, a vector A plus B. So we'd have vector A plus vector B is equivalent to vector that is noted x1 plus y1, comma, or excuse me, x1 plus x2, and then y1 plus y2. And if we're going to represent this addition using these arrows, we'd see that we'd have, so we'll say we have vector A, and that's vector A, and then we have another vector, the other vector, vector B, and so these are the two vectors. And if we're going to represent this addition through these arrows, what all we need to do is really just take one of these and attach it to the end of the other. So say we wanted to add, so we're going to add A and B together. We're just going to take B and attach it to the end of A, or the other way around, doesn't really matter. And then just kind of get the overall vector connecting the new initial point, the new terminal point to the initial point that these two vectors share. So we'd have this new vector, which is vector A plus B, and that's what our sum is being represented by if we were going to put it as an arrow. So A plus B. So we can add vectors together, but we can also multiply vectors by scalars, and scalars in this case are just going to be numbers or constants like 3 or 2 or anything else. So if you wanted to multiply, say, vector A by 3, or multiply it by the scalar 3, we'd have, so 3a, so we're multiplying the vector A by 3, that would be equivalent to 3 times the components of A, which are just x1 and y1. And in this case, the way we multiply is a lot like we multiply using the distributive property, where we just take the outer number and multiply it with all the inner numbers here. So in this case, we'd get the multiplication would yield that 3 times this vector would be 3x1, comma 3y1. So it's really not that different from the distributive property, except you're just using components and using this weird notation. So if you're wondering how we divide vectors, well, we divide vectors the same way that we just multiply vectors, except we use fractions. So if you wanted to divide vector A by 2, we just multiply vector A by 1/2, and then we work it the same way, except it'd just be 1/2 x1 and 1/2 y1 rather than just normal x1 and y1. But that changes when we use negatives, because if we were to use a negative, we'd have to force the vector to flip, and then we'd have a different, and the arrow would look different. So if you were to, let me do this with arrows. So say we have vector A like we did before, and so that's vector A, and if we wanted vector 3a, what we're really doing is we're not changing the direction of the vector, but we're just increasing the magnitude of the vector. So vector 3a is going to have 3 times the magnitude of just vector A. If we're going to have negative vector A, we're just going to flip the vector, so it's going to face the opposite direction. So that's going to be vector negative A. And this is going to be useful when you do not substitution, subtraction. I can't talk. So that's going to be useful when you do subtraction. So that's basically all the different operations you can do with different vectors. And so now we can actually try some practice problems using real numbers instead of these variables here. So we're given this problem that says let u equal vector with components -1, 3, and v equal vector with components 4, 7. Find the following. So 2u plus 3v, which is a mixture of both vector addition and scalar multiplication, and u minus v, which is a vector subtraction. I keep on trying to say substitution, but it's subtraction. And then finally, the magnitude of 1/2 u. So that's the absolute value of 1/2 u. So let's start off with 2u plus 3v. You can pause the video and try this on your own, depending on how long we're going. I don't know if that's going to work, but bear with me. So we can have, let's do a, and so we're going to start off first by figuring out what 2u and 3v are. So we're just going to do scalar multiplication on these two vectors here. So let's do 2u first. So 2u is equivalent to 2 times the values of -1 and 3, which is equivalent to -2 and 6. So just 2 times -1 and 2 times 3. Let's do a different color for the other vectors. So we have 3v. So that's kind of the same thing, where we have 3 times the value of the vector, so 4 and 7. And that's equivalent to 12, 21. And now we just do vector addition. So we just add the two corresponding components together. So we have a new vector with 10 and then 27. So 6 plus 21 is 27. And that's our new vector, and that's the answer to part A. So for part B, we're doing vector subtraction, but this can be relatively easy if you think about it in a different way. So we can think about it, instead of being u minus v, you can think of it as u plus -v. And so this just makes it so that we try to find the opposite of this vector, vector v, and then just add it like we add anything else. So we have so let's figure out what -v is in this case. So -v is equivalent to the opposite of 4 and 7, and that's equivalent to just -4, -7. And now we can just add it to u, because u is unchanged here, and then just get the new value. So it'd be -1, 3, and then we add them together, so we have a new vector, -5, -4. And that's our answer to part B. So finally, we have to figure out what the magnitude of 1/2 u is. So again, we're going to start off by doing all the vector multiplication, the scalar multiplication, and then figuring out the magnitude here. So we do another color. Let's do orange. Yes, orange. So we're going to figure out 1/2 u. So 1/2 u is going to be equal to 1/2 times the components of u, which are -1 and 3, which is equivalent to -1/2, 3/2. So now we're going to use that formula that I showed you a while back to figure out magnitude, since we have the two components now. So that's our a and that's our b. So we're going to take the square root of the sum of the squares of the components. So the magnitude of 1/2 u is equivalent to the square root of -1/2 squared plus 3/2 squared. Let me extend that a little bit. Okay, and so we're going to ignore this problem for now, or forever. We're not doing this problem. So that's going to equal the square root of 1/4 plus 9/4, which is equivalent to the square root of 10/4, or 1/2 times the square root of 10. So that's our final answer. Let me get an actual math, or not a decimal answer for that. So on square root of 10 over 4, and that is equivalent to 1.581. So our magnitude here is going to equal 1.581. And that's our final answer. And that's it, basically, for some basic scalar operations and the introduction to scalars. And I hope that was helpful.